very much, Bob. Another excellent presentation and also right on time. So we'll move right on to the last presenter of this session. Our final presentation is from Mark Sobak, who's the Benjamin M. Cage Professor of Geophysics and the Director of the Stanford Natural Gas Initiative at Stanford University. Mark's an expert in several issues related to energy and the environment, particularly induced seismicity and CCS. Today, he'll share his thoughts on the role of oil and gas in the era of decarbonization.
Well, thank you, Drew, and thanks to the two presenters that came before me this morning. They were really excellent talks and made many good points that I will try to add to. Let me share my screen here and we can get going. The talk I'm about to give is fundamentally not a technical talk. It's a talk, in fact, that Ray heard that I had given to the Society of Petroleum Engineers. And the Society of Petroleum Engineers describes a cohort that you can imagine. Their lives have been, their professional lives have been associated with producing oil and gas around the world. And let's just say that many in the community did not, rush to accept the fact that global warming was a serious issue. Fossil fuels contributed to these issues, and that decarbonization was absolutely critical. What I wanted to try to do was sort of broaden the conversation and talk about sort of a reimagined role for oil and gas, even though oil and gas will continue to play a major role in the energy system for decades to come, as Drew said at the beginning of this session, but also new roles for professionals in the oil and gas industry that are absolutely critical to allow decarbonization to go forward. You know, the need to decarbonize the energy system is sort of beyond dispute for those of us in the scientific community. There's simply no question that we have to do it. The scientific evidence is overwhelming. I don't have to tell you that. And I think all of us, even those who are, say, reticent to accept the need for large scale and rapid adoption of practices and policies that lead to decarbonization, are aware that, you know, just during our lifetimes, things are getting hotter. This is a year ago, excuse me, October 2019, with temperatures approaching 100 degrees in most of the Southeast US. We know where the CO2 is coming from. It's coming primarily from three sources: making electricity, and producing heat, the transport sector, and manufacturing and construction. So we know what sectors have to be decarbonized. And we also know that if you look at the total world energy use, currently 81% is coming from fossil fuels. And if we're talking about electricity, 61% is coming from fossil fuels. So in terms of carbon into the atmosphere, you know, fossil fuels are playing a major role. There's simply no question about it. Now, under this topic then of oil and gas in the era of decarbonization, let me make clear what I'm not talking about. I'm not going to talk about transportation, and, you know, conversion of cars and light duty trucks to electric vehicles is well underway, but the scale is hard to get your head around. There are currently 1.5 billion light duty vehicles in the world, and they stay on the road approximately 11 years on average. In California, where I live, I'm a happy zero emission vehicle driver. There are 600,000 such vehicles, but that's only 4% of all the vehicles. The state goal is to have 5 million ZEVs on the road by 2030, which would require a 25% increase in the number year on year. And that's tough. It's, you know, I don't know if we'll get there. Let's hope we do. I'm also not going to low carbon transportation fuels for aviation and heavy duty vehicles in the future. Hydrogen fuel cells, maybe. Of course, where we're going to get the hydrogen is a question. Biofuels, maybe. Electrification at a larger scale than is now practical because of the weight and charging time of batteries, maybe, but we have no path. We have a lot of good ideas that will, be investigated and play out over the future. And finally, what I'm not talking about is the need for a backup. California has not only a decarbonization goal, but it has a renewability goal. And we have, about 20 gigawatts of solar and wind capability. We have 40 gigawatts of natural gas electrical power generation. And you say, well, we're a third of the way there. We could replace the natural gas. But, the real problem is the utilization factor of that 20 gigawatts of renewables is only about 3 gigawatts. Obviously the sun doesn't shine at night and wind is intermittent. So you have to grossly overbuild, and you still have this need for a backup. And people just haven't gotten their head around the fact that as I've got, completely paid off solar panels on my house. I love it. But it's going to take a long time and to get to scale because of this necessity to overbuild, and we need a reliable backup. And right now, that backup is natural gas, and people just hate to whether it's the public at large or legislators in Sacramento, they have a hard time getting their head around that. So what I'm going to talk about today is the role of natural gas and its ability to greatly improve the effort to decarbonize, principally by decarbonizing the global electrical power sector. There's an enormous quantity of natural gas in various forms around the world, as we'll see. The unconventional revolution that you've heard so much about, horizontal drilling and multi-stage hydraulic fracturing to extract both oil and natural gas from formations of incredibly low permeability. Permeability that is so low, if you've got a granite countertop in your kitchen, the permeability of these so-called shale formations is less than the granite that you put on your countertop. Why did you put it there? Because it's hard and it's impermeable, nothing soaks in. We're getting oil and natural gas out of formations of similar permeability right now. A problem that had been overlooked until very recently is the need for a thermal fuel in the developing world. This is a really pressing issue. It kind of escaped notice until just about 2 or 3 years ago, when you look at the World Bank and other international agencies funding clean energy technologies and energy availability in the developing world. And this is a huge issue that natural gas and natural gas liquids can address. And finally, what I want to focus on at the end of my talk, but perhaps as the most important, is the idea of sequestering large volumes of CO2 in the subsurface has been around for a long time, at least since 2005 and the IPCC report. But what I want to talk about is the scale, the volumetric scale and the time scale that has to be achieved if, in fact, sequestering CO2 in the subsurface is going to be one of the major components of decarbonization strategy that is being used. So we know about the unconventional revolution in the US. These are US numbers. The amount of gas that's been produced in the last decade or so is simply enormous, even though the prices have gone way down. The gas production has gone way up due to efficiency of operations. And corresponding to that, emissions coming from the electrical power sector have declined precipitously down to 1990 or so levels. That's the good news. The bad news, of course, this is data from Exxon, is that the CO2 emission growth that is forecast is going to come from the developing world. And it's largely due to we have about 300 gigawatts of coal generation remaining right now. To put that in perspective, that 300 gigawatts provides about 30% of our electricity in the US, but 70% of the CO2 emissions. But the 300 gigawatts of coal generating capacity in the US is extremely small when you look at the total generating capacity from coal in the US. So in other words, if we were to completely replace coal with, say, renewables, it would simply offset 1 year of proposed coal burning capacity, construction in the rest of the world. Now, these numbers are pre-COVID-19, but roughly 300 gigawatts was under construction, or of it being proposed. Excuse me, a bit more than 300 gigawatts was being under construction and proposed in 2019 alone. And so, a large part of the world and the developing part of the world is relying on coal. Now, they're relying on coal because, as everyone knows, to be a wealthy country, you need to have access to energy. And this relationship between GDP per capita and energy use per capita is well known to all of us. And obviously, the idea is to move up in wealth, to move vertically, and not to move over to the right. But what we can see is historic trends. And as some of these larger countries, of course, India, China has been a case. China's a well-known story by now. But as these countries are getting wealthier, they're relying on energy. As one friend of mine likes to point out, is the difference between a fruit stand and a grocery store is having access to reliable energy. And it's just so permeated through economic development that the two are inseparable. So how do we make natural gas more competitive? If we know that fuel switching works, and we know we have unlimited resources of natural gas, we'll never use it all. We have to distribute it through LNG, which is not cheap. It's cheap right now because of the global downturn, but which might be a bit of a silver lining from a climate point of view, at least for some period of time. But it's not so complicated. And Mark Thurber, an economist at Stanford, has looked at this issue, and in a recent natural gas brief, he looked at the question of, why isn't natural gas in India's climate strategy? Well, the reason is that these decisions are being made strictly on a dollar per BTU basis with no consideration of either climate or environmental impacts. And so coal always wins. So how do we tilt the balance? Well, you put a small price on carbon. And in this one particular analysis that Mark did, a price on carbon of about $22.50 per ton, which is not very much when we think about carbon pricing, that would be enough based on the assumed prices that are shown in the graph to tilt the balance and actually make natural gas cheaper. So it's economically advantageous, it's environmentally advantageous, it's advantageous for the climate, but it requires a recognition that we have to put a price on carbon. You could put a price on the health effects, you can do many other things, but this is one strategy. And the health effects are non-trivial. The premature deaths from coal-related pollution in China is estimated to have been over 366,000 people in 2013, roughly 100,000 people in India, and so on. These impacts are real and need to, they can't be just swept aside when decisions are made about how to provide energy. Let me just say a few words about the unconventional revolution. As all of you know, it's an industry in free fall right now. People toss around words. Companies on the verge of bankruptcy. The amount of activity at the current low oil prices has dropped dramatically. But I think the future is bright, and the future is bright because we're going to need both oil and natural gas for many years to come. The standard technology that's used, horizontal drilling, as illustrated in the cartoon or the sketch, you drill horizontal wells now typically between 1 and 2 miles long. You hydraulically fracture them in individual, what are called stages. This could be done as many, 40 stages would not be unusual now. Some wells have 100 stages, and from each stage, you propagate multiple hydraulic fractures. Surrounding those hydraulic fractures are small microseismic events indicating that small pre-existing faults are slipping, and they are changing these small microseismic events, by the way, are magnitude -2. They release the same amount of energy as a gallon of milk falling off a kitchen counter. They're very small, almost undetectable unless you put seismometers in the subsurface, but their net effect is to increase the contact area between the reservoir and permeable plains and allows the hydrocarbons to be produced. Now, this has resulted in, 5 million barrels a day, for example, of oil production that we have today that we didn't have a decade ago. But a characteristic of all of these unconventional plays, as they're called, the Eagle Ford in South Texas, the Bakken in North Dakota, the Barnett in the Fort Worth Basin, the Marcellus in Ohio and Pennsylvania, West Virginia, the effect of the way in which these things are stimulated and produced is that the rate of production, the average rate of production per well, decreases very rapidly. And in this recent paper, we took this 12,000 wells here in the Eagle Ford, probably a comparable number in the Bakken, 15,000 or so in the Barnett, et cetera. We broke the data into 2-year cohorts so that these are very robust averages. And what you can see is, regardless of whether it's oil, which is the top 2 rows, or gas, the bottom 2 rows, in the first 3 years of production, the production rates decrease very dramatically. And in other words, you've got to keep drilling in order to keep producing. And right now, we're not drilling. Now, if you look at the average cumulative production per well, you can see the curves on the, in the right-hand column. And as a function of time, the different colors represent these different 2-year cohorts. You can say there's been about a 40% increase in the average well production in the Eagle Ford, something comparable in the Bakken, roughly comparable in the Barnett. The Marcellus has been a real success. The average well produces about twice as much. So, one would think that we're getting a lot better at this. But the economics are complicated, obviously affected by the price of oil or gas. That's a difficult thing for the companies to deal with when they can't predict the resource price. It's hard for them to operate in an optimized way. Operational efficiency has increased incredibly. That's really the good news part of this story. All of this happens at much lower prices than I would say with the cost of actually developing these resources is it's more efficient today than I think anyone could have imagined, say, 5 to 8 years ago. So the engineering part of this has been a remarkable success. But the level of effort has also increased. We've gone from 3,000 to 5,000 foot wells to 9,000 to 10,000 foot wells. We've gone to 12 hydraulic fracturing stages in say a 4,000 foot well, to 40 to 60 hydraulic fracturing stages in a 10,000 foot well, meaning, of course, that more fluid, more proppant, and just much more effort. And that's the bad news, because when you actually look at this data a different way, you get a very different story. And so this is from a recent paper. It was presented at the ERCTech conference last month. The lead author is an undergraduate student at Stanford that a colleague, Naomi Bonas, and I supervised. And he was looking at some of these data with sort of, well, the paper stands for it on its own if you're interested. The average production per well has increased. But if you actually normalize this on the average production per foot of well, which is a metric for how long the wells are, how many frac stages there are, and so on, the curve has actually gone the other way. And in fact, the most productive epoch was the very first epoch in 2007, 2008. In other words, we're working harder to get less oil here in the case of the Bakken and these other places as well. And so what we haven't done is we haven't solved the recovery factor problem. We still leave 75% of the gas behind in what are called dry gas reservoirs, and we leave more than 90% of the oil behind in these tight oil reservoirs. And there are many wells that are just uneconomic from the get-go. That's the problem, and that's the size of the prize if we can do these things better. Now, to give you a scale, a sense of the scale of the industry in 2018, for which we have pretty good numbers, there was almost $80 billion spent on horizontal drilling and multi-stage hydraulic fracturing. And the global resource, this slide is a few years old, but the global resource, the light blue color here is all over the world. And the Vaca Muerta play in Argentina is now very active and succeeding. China is very active with gas production in the Sichuan Basin. Australia has tremendous resources, but there's a lot of public opposition to producing gas, which I think are largely fueled by the coal industry. But that's another issue. The way to think about this is many of these formations are the source rocks for traditional oil and gas deposits. It's the organic rich rocks from which the hydrocarbons migrated out into more exploitable reservoirs. That's the conventional oil and gas business. The unconventional business is going right into those source rocks. So almost everywhere that hydrocarbons have been produced in a conventional way, unconventional hydrocarbons can be produced. We are never going to run out of oil and gas. We are going to stop using oil and gas because we're going to decarbonize the energy system. In the short term, what we have is a tremendous need for a thermal fuel. And I think everyone is familiar with the fact that there are literally billions of people on Earth every day who spend many hours. In one conference I attended, the number of 6 hours per day, principally by women and children, for gathering sticks and dung for cooking fuel and for heat. And in fact, there are 3 to 4 million deaths per year. These are numbers of the World Health Organization associated with indoor air pollution. That's more than AIDS, malaria, and tuberculosis combined. Now, either my wife or I took this photograph in the Pamir Mountains of right on the border between China and Tajikistan. It's a village, a grazing village at about 14,000 feet. Only in the summer, of course. And you can see a solar panel, you can see a satellite dish. Okay, that's pretty cool for a bunch of shepherds in a very remote part of the world. But you can also see that they're burning dung for heating fuel, for cooking and heating. And this is a global problem. And progress is being made. India has a program to distribute 50 million propane canisters through developing in rural areas for this purpose. They've not met that goal, but they have distributed tens of millions of propane canisters, and it has an enormous effect on people's lives. This is just an image I got off the web, and so it's just there are billions of people in need of such resources, and in many places, they're already buying energy. So it's not as if, they're having to take on costs that they don't already incur in their everyday lives. Let's talk about CO2 sequestration. And it's kind of hard to get your head around this. I'm going to use some numbers promoted by the OGCI, the Oil and Gas Climate Initiative. International companies, but since 2018, 3 US-based companies have joined the OGCI. Now, these numbers are also the numbers basically that the IEA has produced. So they're kind of a consensus analysis. This next slide was animated, but I'll somehow that I lost the animation. Okay, so let's look at what the numbers are. We're looking at time, of course, on the horizontal axis. These are gigatons of carbon captured and stored. Now, when you look at this and the sectors from which those savings, the CO2 would be sourced and then stored in the subsurface. And that's the goal, is to achieve a 2 C warming scenario that you're all familiar with. Now, when you look at this plot, it kind of looks like a cumulative plot, but it's not. This is the annual rate at which carbon sequestration has to be done. So in other words, if we say that, in roughly around 2038 or 2040, we have to be storing 3.4, 3.5 gigatons of CO2 per year, that's how much we have to be storing then. But, 20 or so years later, we have to be storing, 5.5 gigatons per year. So this is the increase in the annual rate of storage. Now, gigatons of this and, billions of cubic meters of that kind of is a little hard to get your head around when you're converting these different scales. So I put on this diagram a way to think about this more simply. Now, in the subsurface under reservoir conditions, CO2 is supercritical. In other words, it's not a liquid and not a gas, but its density is about 0.6, and it's more like a liquid than a gas. So if you were to consider these volumes in terms of a volumetric equivalent, when we talk about 3.5 gigatons of CO2 captured and stored per year 20 years from now, okay, we are really talking about injecting a volume into the subsurface that's equivalent to the global oil system. Okay, there's about 30 billion barrels of oil that are, produced, distributed, processed, distributed, and then consumed per year. So when we talk about the role of CO2 among, many other technologies that will be used to help achieve the 2 scenario, this is the expectation of what CO2 sequestration must accomplish if it's going to play this key role. We have to be injecting CO2 into the subsurface at a scale comparable to the global oil system in 20 years, and at twice that scale later in mid-century. It's just an enormous volumetric scale, and it's an enormous pressing time scale. To put this in perspective, a number of projects, a couple dozen projects around the world are operating roughly at the 1 million ton per year level. And so this is where we are today. I should move this arrow. I made this plot about 18 months ago. I should move this arrow to the right, but we're basically not off the horizontal line. We're 30 million tons. So we're really talking about a 1,000-fold increase in a 20-year period. Shell has undertaken its own look at sort of decarbonization strategies. It's an all of the above kind of a strategy, but they're in their assessment looking at how much CO2 has to be stored over what period of time. It's really quite comparable. The details are different. They're at 1.5 times global oil production by 2050, but the message is still the same. The scale at which CO2 has to be stored in the subsurface in a relatively the IPCC report in 2005. We have depleted oil and gas reservoirs. We have what are called saline aquifers. These are sedimentary formations in the subsurface that are filled with brine. Not, they don't have oil in them, and because it's saline, these have never been produced. They're just known to be there, and they're possible places to put CO2. And there's some other opportunities as well, but basically depleted oil and gas reservoirs and saline aquifers are the two main storage options. Now, in the US, most of the work that's been going on for the last 15 years related to storage of CO2 has been investigating potential saline aquifers in different parts of the country. But what has become abundantly clear over about 10 to 15 years of research is that there are enormous challenges. First, you need totally new infrastructure, right? That's going to take time to develop. The cost is enormous when you start talking about gigatons on a global scale. Key questions like liability and the need for monitoring and potential remediation, in other words, creating a regulatory environment, has really not been done yet. And the difficulty of obtaining and maintaining a social license to operate is simply enormous, and at the very least takes a great deal of time, and in many cases actually will stop projects dead in their tracks. At a session at last year's SPE meeting that was discussing these kinds of things, one participant showed a pie chart indicating 15 stakeholders that would kind of weigh in on the suitability of any proposed site. The geologic challenges are not to be ignored. The pore space is already occupied. In other words, in a saline aquifer, for example, it's full of salt water. So if you were to put in CO2, the pressure is going to go up. And these required volumes are extremely large, and pressure management is an extremely important part of the overall picture and has to be done. And when you're dealing with a saline aquifer, you have to remember that nothing about this. In other words, there's been no geologic characterization because there was never an economic driver. It's there, but from any kind of characterization perspective, you're really starting with a blank sheet of paper. On the other hand, and where I'm coming from is I think that the only way these massive amounts of CO2 can be stored in the subsurface, in timescales of the next few decades, is to use depleted oil and gas reservoirs. We've been creating that needed pore space by producing oil and gas, for the last 100 years or so. And so we've created, we sort of have pore space in the bank, if you if that metaphor makes any sense. The oil and gas industry has tremendous knowledge of the subsurface. There was an economic driver. These fields were studied with the very best technology by the very best people for many decades. Much of the infrastructure is already in place, but not all of it. And that's a real issue in assessing how suitable existing wells are, pipelines, et cetera. Some of that will have to be rebuilt. Some of it could provide a leakage hazard. And so it's not a slam dunk. But, there's a lot of focus on enhanced oil recovery. That's, a subject unto itself. And I'm just going to leave that aside for right now. But what I'm saying is, you need a place to put it. You need a place that is already sort of an industrial site, and you need the opportunity to inject large volumes without creating tremendous increases in pressure. And if you are working offshore, the regulatory system becomes much easier because you're working, in fact, with a single regulatory entity. It might be a given state, or it might be federal, but nonetheless, the regulatory process is much more straightforward, which could be, when we actually stop and think about it, could be the single largest impediment to moving the Society of Petroleum Engineering community is that my view of the oil industry, of the future, is that it's going to, we're going to continue to need oil and gas for decades to come, as everyone has said and is widely recognized. But we're also going to be decarbonizing at the same time, and the traditional role of the oil and gas industry is going to be slowly diminishing over this century. At the same time, as that curve is going down with time, the curve that has to go up with time very dramatically is to be storing massive quantities of CO2 in the subsurface. Depleted oil and gas reservoirs are the best place to put it, and it has to happen at this enormous scale. And the only entity that can actually accomplish this is the oil and gas industry. And I think it would be very beneficial for the industry, not only in how they're viewed by the public, but in attracting talented young people to work for them, is to be, legitimately part of the solution and not just part of the problem. I think to date, there have been a lot of pilot projects, a lot of hype that are more promotional than substantive, but it's time to get serious. And the oil and gas industry is well positioned for this, and I hope they are willing to take up the challenge. And with that, I'll thank you, and I'm happy to answer your questions.
Thank you very much, Mark. That was really motivational, at least for those of us who are also SPE members. So let me get right into the questions here. So the first one talks about the economics. So the question is that the collapse of the unconventional companies was in the works for a long time because these companies were highly leveraged and the pandemic exposed these weaknesses. What steps can the business take to restructure and better compete in a post-pandemic world?
Well, I don't know much about economics, but it really was an industry fueled by debt. And I'll tell you just a brief story. I was talking to an operator who was very active in the Bakken. And he said, well, we're shutting down our last rig. This was a couple months ago. And I said, and the oil price at that time was like $45 a barrel, okay? And I said, you mean you can't make money at $45 a barrel? He says, oh, no, we make money at $40 a barrel. So I said, so why are you stopping operations? He says, because we can't borrow any more money. And this whole industry was fueled by debt, and these companies took on so much debt. I think it was really irresponsible. And the irresponsibility was on both sides. Those people who were willing to invest in these companies, and the companies themselves for kind of operating those companies in an irresponsible way, so that when the oil price dropped, they're stuck, right? So the way I see it is we need to work smarter. We have to improve the recovery factors, and the industry has to kind of regroup and move forward with a smarter business model. And I think what's going to happen, this is just a guess, is that the larger companies, the majors, are going to kind of be scooping up these little companies and their assets as the companies go under, and then the industry will have a restart with a better operating model from an economic point of view that will allow them to weather the inevitable variations in the oil price. But you should ask an economist. They could probably explain it to you better than I can.
All right, I'm going to ask you two short ones and then one kind of long one. So first short one, on slide, so the question references slide 15, which was the plot of the per capita GDP against the per capita energy consumption.
Yeah.
And the question is simply, where does the USA show up on that plot?
Good question. We're way off on the right. I'm looking for it right now. I should have asked myself that question. I think I know. Here, let me share my screen again. It's not labeled, but I think by default we can find it. I think this big circle right here is the we're up high. We have a large population, much larger than Canada or Australia, and our annual energy use is quite high as well. So I think that's the US right there.
Very good, thank you. And then if you could keep your slides up, the next one on slide 20, I think that's the one with the decline curves. The question is simply, when is the fracking capacity exhausted?
It's never exhausted. You know, the Bureau of Economic Geology at the University of Texas did a study a few years ago. And the assumption of the study was the question of the study was how many wells might be drilled in the lower 48 if we restricted drilling to where drilling is already allowed. So you don't have to open up national parks, you don't have to drill on the playgrounds of elementary schools or in metropolitan areas. So we'll only drill where drilling is allowed. We'll only drill into already identified productive horizons. So we're not basing any extrapolation on you know, future discoveries. In other words, the geologic discovery has already been made. Because of things like what are called stack pay, that's multiple producing horizons at the same geographic location. This is largely the case in the Permian Basin of West Texas. This is why the Permian has been so active for the last few years. The number that the Bureau came up with, prepare yourself, is 1.6 million wells. Now the number, it doesn't mean anything, this number. Obviously, the price of oil and the cost of extraction will modulate that number, but the number is irrelevant because it just means that you know, for as long as we need hydrocarbons, we have resources available to us. And so this idea of, you know, running out of oil or gas is just nonsensical. Now, you know, of course, public opinion is shifting very rapidly, and we're seeing, you know, a state like Colorado that was, you know, an oil-producing state in which environmental and oil and gas interests were living in, if not in harmony, in some sort of balance. But, you know, things have shifted very, very rapidly, and, you know, oil and gas operations are threatened almost everywhere. Could this happen in California? Could this happen in Texas? It's not inconceivable. It's not going to happen overnight. But so the resource is unmeasurable and infinite. We will decarbonize our energy system long before we run out of these resources.
Thank you. And so the last question we've got here is about hydrogen and talking about the role of CCUS in generating blue hydrogen, where the hydrogen comes from methane and carbon is buried. So the question says, to be optimally successful, this process must take existing values like technology and finance from the oil and gas sector to make the energy transition easier and quicker. So why should anyone, including government policies, consider green hydrogen for renewable power and electrolysis, given that it is a very expensive venture?
Well, so there's just so everybody understands, when we're talking about blue hydrogen, we're probably talking about using techniques like steam methane reforming, well-known techniques to make hydrogen from methane. When you do that, and that's been done for many, many decades, but when you do that, you produce CO2. So green hydrogen is associated with electrolyzers that are using, you know, no cost electricity because we have so much so much renewables. And when, you know, demand is low, you're just, you know, it's, you know, a penny per kilowatt hour or something, and you're electrolyzing water and you're making hydrogen. I think, you know, any strategy that has hydrogen as a centerpiece of an economic sector, you know, requires feasibility. And so I think in many people's mind, we go to blue hydrogen to see really is hydrogen going to be, you know, a viable alternative, you know, hydrogen fuel cells for large scale transportation, et cetera. And so blue hydrogen is sort of a stepping stone. which you know hydrogen is viable as a fuel. And viability means, of course, widespread use under you know, realistic operational conditions and costs. The stumbling block for blue hydrogen, the only stumbling block, is really what do you do with the CO2? And there's a bit of a cost. So the way I look at this is I look at it backwards. I don't say, well, we want to do SMR here, and so what do we do with the CO2 at the site where we're going to produce the hydrogen? I look at it the other way. Let's find a place that's ideal for CO2 sequestration and put the SMR there. And that way you start by solving the hardest part of the problem, because the rest, you know, I don't want to make it sound easy, but we know how to do it, right? We know, you know, pipelines are a potential problem for hydrogen, but we could probably make polymer-lined pipelines to transport hydrogen. SMR is not, you know, as efficient as it could be. There's a lot of people working on making it, you know, better. You know, how is hydrogen being used? Well, there are lots of places and companies involved in hydrogen transportation systems. Hydrogen is potentially, you know, available to the power sector, in petrochemicals, fertilizer, for example, everything. So we know the market is there. The real stumbling block to blue hydrogen is, what do you do with the CO2? And so it's part of this same kind of question we're asking generally about CO2 sequestration. So anyway, the way I would approach, you know, the path to discovery with a hydrogen economy is to start making hydrogen at scale and just see how the marketplace and technology and all evolves. And to do that, we need to sequester the CO2. And so if you can solve that problem, the rest is downhill. It doesn't mean it's going to be easy, but it's better than going the other way and finding yourself with a 10-year effort to get an injection site approved, or possibly not.
All right, thank you very much. So we're a little over time here, so I think we'll wrap it up now. I'd like to thank Mark and all the presenters and all those who put in questions. I'd say for a meeting about renewable energy, this session on oil and gas worked out pretty good. So so happy about that. We'll conclude things now, and maybe the conference organizers have some announcements.
Thank you very much.